Hello students, today I'm going to interact with you for the ADS subject Advanced Data Structures for the second years of JNTK syllabus. Here I'm going to discuss you the introduction of multi-way search trees. So why we are using multi-way search trees? What is the need for multi-way search trees? So in this session I'm going to teach you what is the need of M-way search trees, as well as B trees. Here we go. Here, what is the need of M-way search trees? We already know that when we have to access the stored data which are present in our computers, we cannot directly access the data from the hard disk. So we have to access through its RAM. Then RAM will access through from this tertiary storage device, which is called hard disk drive. So hard disk contains this structure, which will contain the blocks as well as sectors and tracks. Here this is the tracks 0, 1, 2, and this is a block, and this is the sector. Whenever we want to access the block address, we need to know the sector number as well as track number. For the block address, track number comma sector number. So here sector number 0 and track number 0. Here is the block. This is the block. Sector number 0 and block number 0, track number 0. This is the block, which will be numbered as block 01, and sector number 0 and track number 1, this is the another block, which will be named as 1, 1, and sector number 0 and track number 2, this is another block, which may be 1, 0, whatever we want. This is a rough addresses. Block address can be defined with the help of sector number as well as track number. So what is the block size? For physically for every block has 512 bytes, and every byte has its own address called offset. The offset can be, this is called offset. This offset can be located with the help of track number as well as sector number. This is the offset representation, that is 0 to 511. We have the 512 bytes of block size, so 0 to 511. Here is the disk structure. This is the disk structure. Here these are the tracks and these are the sectors. This is the pointer that may called read or write head, and this is a spindle. Whenever the block has placed on the spindle, it will rotate, and then read and write head will read or write the data which are present on the disk. The disk will rotate slowly, and this read and read head will read. Whenever the disk will rotate, the track number as well as sector number will rotate as well, so it will change. So likewise, this is the clockwise direction or else anti-clockwise direction. The disk will usually rotates from clockwise direction, so here it will rotate from one sector to another sector as well as one track to another track. We have seek time and latency time here. Let us know about it after our introduction. So here the disk is placed on the spindle, I already said that, and it rotates. Then the head pointer reads block by block. I already explained you about the block. So this is the disk structure. In the exam, you have to draw this disk structure roughly. Don't need colors as well as disks, not like that. You can roughly draw this disk structure. Data cannot process upon the disk. I already said that it is an indirect process, it is not a direct process. So firstly, data is processed in RAM memory and it will write upon the disk. whenever we want to store the data in the hard disk, firstly it will copied or write into the RAM memory, that is the random access memory, which is the temporary memory or main memory which we call. So and then it will write upon to the hard disk. Whenever we want to access the data which are present in the disk will access from the data disk to random access memory, and then we can access it. This is a tertiary device. So for accessing the data from the disk to main memory and then to access it is very large process. So in this, for the data storage in disk we use DBMS, database management system. For organizing the data, in RAM, we are using our data structures. For organizing the data in database, we can use database management system. In the database management system, data can be stored as records, which will be stored in table structures. So in the database, how can the data is organized in database? Let me check about that. Here these are all the records of an employee. This is the records of an employees which were in a company name, for example X. For X company, these are 100 employees are there for each department, accounts management, etc. So for this 100 records we have to store this in our database, that is disk. So how can we store it into the disk? Here are the employee ID, name and department, as well as it may add employee salary, as well as their address, as well as phone number, whatever. There are so many fields. So in these records, so we have to store it to the disk. So for example, these are the employee fields, that is employee ID, name, employee department, as well as employee salary, as well as employee's address. So employee ID may take 10 bytes, and employee name may take 50 bytes, and department may take 10 bytes, salary may take 8 bytes, as well as address may take 50 bytes. So totally one employee record may occupy 128 bytes. So for the storage of each record of 120 bytes, we have to need 128 bytes. As we said that each block in the disk structure will contain 512 bytes. So for each block we may store 4 records, that is 4 into 128, sorry, that is 512 bytes. Number of records per block, that equal to 512 by 128, that is 4 records. For each block we may store 4 records. Here this is one block, that is 0th sector first track. So this is the 0th sector first track. This is the block 1. Block 1 may contain first 4 records, and then block 2. Here is the block 2. This is the first sector first track. So one track may contain block 2, that is from 5 to 8, 7, 8. This block 2 may contain another 4 records and up to 100 records. So each block may occupy 4 records, store 4 records. For 100 records we need 25 blocks. So here for the day in the disk we need 25 blocks for storing all these 100 records. So that is this. We need 25 blocks. If you want to access the 95th record which were present in data, which were present in the disk, so whenever we want to access the 95th record may be present in which block? Here we have 25 blocks. So in the 25th block it may have 96, 97, 98, 99, sorry, 97, 98, 99 and 100th record. So in 24th block we may have 100th record. For example, if the read and write head is present in the 0th sector or first sector whenever we store this record, or else if this is a empty disk, hard disk, we may try this with our oral representation, or else if already some data is present in the hard disk and then we are going to save this another data of this company X, so we didn't know about the pointer head which they were present in the block. So that entire block, when we want to access the 94th employee record, which will start from the first block, and it will rotate as well as it will read all the data and then seek the data block size which there, if 95th block is present here, so it will read entire the disk and then it will go to the 95th block, and here we may access the 95th record of an employee and their details. So this may take so much of time from passing this to all the records as well as the data which were already stored in the disk. So to reduce the time, if you want to access the 95th record, then we have gone through all the records which were present in the disk blocks. It's very process. It's very slow process. It's very easy to say like this: block 1, block 2, block 3 and so on, but it's very slow process, very slow process. So to reduce the time for searching, we are going to prepare index for this record. Here we are preparing the index. Likewise, for example, our textbook. Our textbook may contain the index page which will present the chapter names: chapter 1, chapter 2, chapter 3. Chapter 1 may contain different number of contents. Chapter 1 may contains 1.1 topic, 1.2 topic, 1.3 topic, 1.4 topic. But chapter 1 contains all these topics, as well as chapter 1 page number from 1 to 30 or 1 to 50. Example, this is our index page of textbook. This is the first chapter. First chapter may be multi-way search trees, and here are the different definition, properties, as well as B trees, operations, as well as B plus trees and operations. This is 1.1, this is 1.2 and this is 1.3. Here multi-way search trees topic will start from 1 to page number 50 here, and the definition and property, and this may divided from 1 to 10. This is the index. And which is also we have another chapter. For example, this is the digital. For example, this is the digital search structures. Digital search structures. So which may be the 51 to 90, and this is also may have, 2.1, 2.2, 2.3. So from 51 to 90, this much details are there. So here we have taken the index here as well. Here this is the index of an employee. This is the index of an employee. It is the index which were created. This is the employee details. So employee id and pointer to the employee id. So we are taking the page number, like with our textbooks example, page number. That means the block number or the pointer where we have to go. Here the disk. So here we prepared index for all the records. Directly we can go to that index and search for the employee id there. For example, so to store all the index details also, we may have to prepare another data. That is, for example, if the index we want to store in the employee id, we have to store the index also stored in the disk. How much space it will take? Employee id is 10 bytes, so record point may take 16 bytes. So 16 bytes, entry size is 16 bytes. Number of entries per block equal to 32. So for each entry of an employee id, 32 bytes may take. So we require, for 100 entries, we require more than 3 blocks for indexing. So already we want 25 blocks, and as well 4, another 4, another 4 blocks, or 3 or more blocks, that is 4 blocks and 29 blocks. Let us consider 4 blocks we require to store an index. For accessing any record, we have to access the index of 4 blocks and then pointer towards to the record. If we want to access the 95th record, here the pointer 95th pointer may be present here. So 95th, directly we can go to the 95th which were present in the pointer address, then it will directly go to the 95th record. So here for storing the index, we have to allocate some more blocks to the index, as we already explained that. But it is also a time taking process. Here the index, if 95th employee id, we have to compare from 1 2 3 4 5 6 and so on 95, and 95 to here the 95th pointer, where 95th, somewhere is there, and then we access. That is also a very slow process. So here for storing the index or for reducing the time, we may add, whenever we want to search for the record, or else whenever we want to access, for accessing any record we have to access the 4 blocks. So for 4 blocks indexing, for any record we have to go on through that 4 blocks. It will reduce the time when compared to last explained one, only the records and the disk. For example, if we add one more record or one more index, that is called multi-level index, instead of 100 records we have 1000 records, then we require 250 blocks to access for the records. So we have to access the all the 40 blocks. Here one more index will be created for the 32 bytes of index pointer will be stored, and then space index. Let us see what is the one more index, or else multi-level indexing. Here is the one more index. Here we will take the 32 bytes, that is 1 to 32. 1 to 32 may be gone through this 4. Here 1 to 32, and then 33 to another 32. That means 64, 63. So that will go to the next 4 records. So from 1 to 32 bytes, first 4 blocks will be there, and then 33 to 63 another 4 blocks, as well as likewise we will go on through the index. Here here this is the multi-level index, and this means 1 to 5. This is 1 to 5 to 10. This is 10 to 15. This is 15 to 25. This is 25 to 30. This is 30 to 50. So like this we have gone through all this. This is the one more index which we have added, and then that will go to the 1.1. if you want to go to the 1.1, then we directly go to the 1.1 to 5 pages. We will access 1 to 5 pages, or else we have gone to the 1.2, then we go to the 10 to 25 pages. First B trees is the first one, then operation, so we will directly go to the 15 to 25 pages. Then here also 1.2.1 something, here also 1.1.1 something, here also 1.3.1. if one more thing properties were there, then 1.3.2. so directly we can go through this. So to reduce the time, another multi-level indexing. There is a first index and then second index, so directly we can access through this. When we this is the rough structure of the multi-level indexing in the database. When we rotate through this, let us see how it will represent. It will represent like a tree structure. This is the root one, and this is the children, and one more children. This is the levels, level 0, level 1, level 2. This is like the tree structure. So multi-level indexing, adding multi-level indexing will reduce the number of blocks to access. Here to self-manage the data. Here we just know the problem, and we just find the solutions for indexing. So to self-manage the multi-level indexing, we need B trees and B plus trees. That is multi-level indexing, and the concept of M-way search trees need as well as B trees. Multi-way search trees. How can it will take? We'll discuss in another session. In this introduction, we may have 2 marks questions. Likewise, what is the latency time and what is the seek time, as well as what is the disk size. Here this is the seek time. Seek time is defined as the time required by the read or write head to move from one track to another. For example, here let us take here read and write head was present in, this is the sector 1, sector 2, as well as sector 3, sector 4, sector 5, and this was present in the track 1. This is second track, this is third track. So this read and write head was present in track 1. Then we want to go to the track 3. So then from track 1 to track 3, it will rotate, and then go to the second block, and then go to the third one. So to reach this read and write head from this to this, we need some time. Then we may want to read the track 3. Here track 3, track 4 was not there. So then the time it will take to reach track 3 is the seek time. Here this is from this to this, read and write head. This is the seek time. What is the definition of seek time? It may be asked for your exam, semester exams, as 2 marks question or 3 marks question. We want to represent like this. Seek time is defined as the time required by the read or write head to move from one track to another. This is the read or write head to move from the one track to another. What is the latency? Latency is the average time for the sector being accessed to rotate into position under a head after a complete seek. Here from one sector to another sector, it will complete the block, read or write complete block, as well as it will change from the one track to another track. So the average time which will take to change from one track to another track. The sector rotation, from one sector to another sector rotation, the time being which were accessed by, or else taken by the read and write header position, which is called latency. Latency is the average time for the sector being accessed to rotate. That means from one sector to another sector, changing the read and write head, the time it will take, the rotation of the sector rotation time, which was taken from the for the read and write head to access the disk, which is called latency. Here head was located in sector 2, and then after the completion of the seek, it will read and write another sector. So sector 1 to sector 3, as well as if sector 1 to sector 2, sector 3, sector 4. This will average time. This is the one more question: what is the seek time, as well as what is the latency time? Seek time is the one track to another. Latency time is the one sector to another sector. What is the block size? I already discussed you about the block size. Block size is 512 bytes physically. So the physical block size in 512 bytes, which is the size of smallest block that the disk controller can read or write. We already know about the block size. This is the block. This is the one more block. So this is 512 bytes, as well as this is 512 bytes. So this is the physical block size, as well as this is the smallest block that the controller can read or write, is a head pointer that may be write or read. This is all about the need of the MV search trees and B trees. Hope you guys will understand the introduction. Let us discuss about MV search trees, and we'll discuss about the MV search trees as well as B trees in another session. Thank you, and please study well for your exams. Is there any doubts? Please ping me, or else comment in the comment section.